Greetings again, everyone, and my name is Franz, and welcome to today's session. We will be continuing with organic chemistry and the naming of the different types of homologous series. In the previous session, we did naming of the first four homologous series, which is alkane, alkene, alkyne, and haloalkane. So today we will continue from aldehyde up until the last one, which I'm going to make it to be ester. For some reasons you will be able to understand as we get to that position. Buckle up and then enjoy the session. So we will be starting with aldehyde, and I'm going to write the stem or the suffix, or rather, sorry, the prefix stem, just to remind ourselves of the things that we spoke about previously. So the stem will be having 1, 2, 3, 4, 5, 6, 7, and 8. And all of these represents the number of carbons, meaning if a carbon chain has 1 carbon, it's going to be called meth, 2 carbons, eth, 3 carbons, prop, 4 carbons, bute, 5 carbons, pent, 6 carbons, hex, 7 carbons, hept, and then 8 carbons, oct. For caps and then grade 12, we are allowed only to teach you about the last number of carbons on the longest chain in the carbon chain is 8 carbons. So now let's remind ourselves of the functional group of aldehyde. We said it is the carbon bonded with a double bond to oxygen. Carbon double bond with oxygen, and it is always on the first carbon. The functional group of aldehyde is always and always on the first carbon. So this is a representative or representation of the functional group of aldehyde. So we can put as many carbons as we want up to until 8, or we can just put a hydrogen, is up to us, so long as it's only on the first carbon and then closed by a hydrogen. So let me try to make an example with a particular structure. I'm going to say 1, 2, 3, 4, and 5. And then I put my functional group here. And then I put all the hydrogens such that I can make sure that my structure is fully serviced or bonded. We can name it. Now let's check. The first thing that we need to check is the number of carbons such that we can get our stem or the prefix. And then we are going to count from the carbon that is bonded, or rather the side that has the functional group getting the smallest possible value. So meaning which is this side, which is from right to left. 1, 2, 3, 4, and 5. We find that our carbons in the longest carbon chain is 5. So meaning our prefix or the stem is pent. So we'll be saying pent. Pentan. And then what is the suffix of aldehyde is al. So the name of this thing is going to be pentanal. Why pentanal? Pentan meaning 5 carbons, and then al or al meaning it is the suffix of an aldehyde. It shows us that whenever we see al, we know we are going to talk about aldehyde. Irrespective of how long the carbon chain has, or rather is, it shall always be like this. There won't be any numbers being put in between the pentan and the suffix, as you remember when we were doing alkene and alkyne, we had to create a space in between the prefix and the suffix. But in this case, there's no need for us to create that particular space because the functional group is always in the first carbon. I hope it makes sense. So let's come to do the second one, which is ketone. Ketone. If you remember well, I said to you, ketone and aldehyde, they share the same functional group. But the difference between these two is that for aldehyde, its functional group is always on the outside, meaning on the first carbon. But for ketone, its functional group is always in between two carbons, meaning it's surrounded by the two other carbons, something of this nature. So meaning this is the representation of the functional group of ketone. It is there and it is surrounded by two other carbons. Let's add hydrogens there. So now we check how many carbons are there that makes the chain. We see this 1, 2, and 3. So giving us that the prefix is going to be prop. But what is the suffix of ester? Of ketone is 1. See? So even if we count from this side 1, 2, 3, we can see that the position of the functional group, if we count from the right hand side to the left hand side, or from the left hand side to the right hand side, it always gives us 2 if the numbers of carbons from the left and right are equally given. So now what will be the name is going to be propan, and then we hyphenate and give the position of the functional group, which is 2, propan 2 on, or rather 1. But pronunciation of this one is like when you say you switch something on, so it's going to be propan 2 on. Good. And then let me make an example whereby there is there's no equality with regards to the number of carbons in this side or that side. So let's say we have 1, 2, 3, 4, 5, 6, and 7. And maybe I'm going to put the functional group here, and I have everything lined out like that. So it's going to be like this. And remember, one other thing, important thing that I mentioned in our previous session is that the carbon has to bond with a maximum of 4 because of the valence electrons of carbon. It is 4. Cool. And then now let's start to count. Let's count from right to left. We have 1, 2, 3, 4, 5, 6, 7. We are done with the first part of checking the stem. But now let's count from left to right. 1, 2, 3, 4, 5, 6, and 7. Still the same. However, the reason why I wanted us to count from both sides is to check which position of starting to count is going to give us the functional group having the smallest value, or rather smallest possible value. From right to left, you find that the functional group is going to be from on carbon number 5. But from left to right, the functional group is going to acquire carbon number 3, which simply means that we're going to take the one that is low, or rather smallest between 3 and 5, which is here 3. And then we come here, we find that we will be having hept. So the name will be heptan. The position of the functional group 3, and then the suffix of the ketone, heptan 3,1. So, or on. So this is basically the IUPAC name of this particular given structure. So you need to be very much vigilant when it comes to you numbering. You need to remember you number from the side that is going to give your functional group the smallest value compared to the other side where we will be basically having to name or number from. That one is for ketone. And then let's proceed. And then start to do alcohol. And then here in alcohol, I'm going to just gonna erase this part. And then I will be doing something that shows the relationship between an alcohol and haloalkane. Just after I showed you how do we name alcohol. Alcohol. And remember, I said to you, alcohols, you can put its functional group on any other carbon. Any carbon. You can put the OH on any carbon. So meaning the functional group of alcohol is OH. I know some people like to write it like this, C, and then they put OH like that. Please, according to me as my advice, please refrain from writing it like this. Show all the bonds when they say to you draw the structural formula, because the purpose of the structural formula is to show all the bonds that are existing in between all the elements that are there. So this, yeah, it's fine. The examiner can give you to you like this, but you yourself, you do not do this one. You do the one that I just shown you on top here. Make sure that all your bonds are visible such that we do not guess if that is a hydrogen or what, we do not know. So make sure that they are all visible. First things first, we check the number of carbons. As I've explained prior, we count from the position, or rather the carbon closest to the functional group. In this case, the functional group is in carbon number 1. So we'll be starting counting from here. 1, 2, 3, 4, and 5. We are told as the number of carbons are 5, meaning the prefix is going to be pentan. And then in cases like this, you can say pentan 1 all or pentanol only when the functional group is in carbon number 1. So for those who do not want to jinx their life, you can just put the position of the functional group and say pentan 1 all or pentanol. Because by writing pentanol, we know exactly that simply means that the functional group is on carbon number 1. Even yourself, when the examiner has given you pentanol, when you draw the structure, you know that the functional group is on carbon number 1. I hope it makes sense. Now, it comes to that time whereby I want us to do the relationship between alcohol and haloalkane. Alcohol and haloalkane. Let me just erase here in the middle such that you can get enough room. Alcohol plus haloalkane. The first stage of your education prior to preschool is called primary school, meaning stage 1, from Latin primus. And then the second stage is secondary school, also from Latin secundum, meaning 2. And then the last stage, or rather the third stage, is tertiary, meaning tertiary, meaning third stage of your education. So even here, we will be having primary alcohol or haloalkane, secondary alcohol or haloalkane, tertiary alcohol or haloalkane. Both of them, they follow the same logic. I'm going to show you here. I'm going to use P for primary, S for secondary, T for tertiary. And then I'm going to draw the structures that belong to all of the three. And then we see what is basically happening. So primary alcohol have the functional group on the carbon, like the carbon bonded to the functional group is bonded only to one other carbon. Carbon bonded to the functional group is bonded only to one other carbon. And then the carbon bonded to the, for secondary school, secondary alcohol or haloalkane. Let me show you as I draw this stuff. It will be like this. So if I draw the structure 1, 2, 3, for alcohol, we'll be having OH. Want it to be clear. Then even in here, I'm gonna say 1, 2, 3. And I'll choose any of the halogens. Doesn't mean if I chose bromo, we're only going to use bromo. So we can choose whichever. Oh, sorry, no, that's not primary. Now let's check. The carbon bonded to the functional group here and there is bonded also to one only carbon, meaning carbon bonded to the functional group is bonded only to one carbon, meaning it's one for one. That's why we say primary, because it's only bonded to one other carbon. I'm just going to change with regards to halogens such that we can get variety. And then we have this. So look at this part. The carbon bonded to the functional group on both sides is bonded to two other carbons. We are focusing on the carbon bonded to the functional group is bonded to two other carbons. That basically gives us what? Tertiary, or rather, sorry, secondary alcohol and secondary haloalkane. Let's look at tertiary. I think for now you should be getting the whole idea of what is happening. Let me use iodine, or rather, let me bring it here. 1, 2, 3, and then I use iodine, or rather iodine, and then I use C, hydrogen, 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 and our beautiful hydrogens. Now, let's come to tertiary. We realize we have our functional group here, and look at the carbon bonded to the functional group is bonded to three other carbons, meaning tertiary. Functional group is there. The carbon bonded to the functional group is bonded to 1, 2, 3 other carbons, making it what? Tertiary alcohol. This is basically the whole idea of how we can see primary, secondary, and tertiary alcohol and haloalkane. That's the relationship between these particular three two homologous series. Examiner can give you a structure, a name, and ask you afterwards to name this alcohol and then tell us, is it a primary, secondary, or tertiary alcohol based on what you will be seeing. It basically has to be like this, and then you will be given full marks if you were to follow this particular um, structure. And I hope I made it simple as possible, as it can never be. And then, yeah, that's basically that. Let us proceed and do carboxylic acid. So carboxylic acid behaves similarly with, it has similar traits with aldehyde, because its functional group is always on the first carbon. So carboxylic acid, its functional group is C double bond O compound, bonded to another O and then an H. On the side, we can add as many carbons up to the eighth carbon as we want, or we can add a hydrogen. It's not a train smash. However, it is always closed by a hydrogen on the other side. So even like the aldehyde, the name of this particular functional or rather homologous series, there is no need for us to put or rather write its what you call this, its position. We can just say propanoic acid, hexanoic acid, whichever way, whichever we, according to the number of carbons in that structure. Let's do a practical example. 1, 2, 3, 4, 5. Now we check. We're going to start counting from the side that the position of the functional group is at, which is right to left. 1, 2, 3, 4, 5. So now by having this, we now have the understanding that we have 5 carbons, meaning the structure will be starting with pent. So the structure is going to be pentanoic acid. So that is the IUPAC name of the structure, pentanoic acid. And then that's what we can do in this structure, because there's nothing else here besides the 5 carbons and the functional group. That's what we do, and that's how you name the basic structure of carboxylic acid. And that's that. We can go to ester. But with ester, I'm going to do something beautiful. I like to call it like that, because a number of people like to prefer to do it when we do organic reactions. So myself, I find it helps you to understand where does ester come from, and then how easy you can do the naming of ester. So it's like this. It's going to be called esterification is a process. Esterification. So esterification in this case is the process of forming an ester. Process is a reaction, as I explained. Process of forming an ester by doing what? By reacting an alcohol with a carboxylic acid. But there is a reaction condition, or rather reaction conditions. Acid in the presence of heat and the catalyst. A catalyst called sulfuric acid H2SO4 to form exactly ester, as I explained on top, and an inorganic compound, an inorganic compound called water, H2O. So meaning the reactants are here. The reactants that we will be having is alcohol and carboxylic acid. The products will be an ester and water. That's basically the whole idea that is happening. If I were to put it in perspective, I can say alcohol plus carboxylic acid. I'm going to put the yield sign going out down. We have ester plus water. The reaction conditions, I'm going to use the enthalpy sign to show heat, and then here I'm going to use H2SO4. This is basically how you're going to show the process of forming an ester. And then one of the important things that you need to note here is this. The carboxylic acid carries the suffix of esters, of an ester. Carboxylic acid, I will show you how, carries the suffix of an ester. Remember, the suffix of an ester is weight, O-A-T-E. And then the alcohol carries the branch part, carries the branch part of the ester name, which is what? The YL. The branch part will be ending with YL. So just to make an example, so that when we get to that naming, you'll be able to see how easy it is. Let's say the name of alcohol of carboxylic acid is methanoic acid. And then for alcohol is methanol. So the name of this ester that is going to be formed here is methyl methanoate. As I said on this bullet, alcohol carries the branch part. So this is going to be methyl, and then this is going to be methanoate. You see, so the alcohol takes the branch part, and then we start with the branch part. Hence, I'm saying we're going to start with the methyl and then end with the methanoate part. So let's get to business and show you how we get to understand the naming of this thing. Is beautiful stuff. And as you can see, there's not much of things. There's nothing basically that is changing, because now we are on the 9th homologous series, and then we started on the first one, alkane, and then the rules are basically the same, or are independent according to each and every homologous series. So let me do an example with that methyl methanoate. Let me say plus now let's check. The first thing that you need to know is to remember that one of our products is water. So in this reaction, I have to take out water from this reaction, meaning I have to take these 2 hydrogens and 1 oxygen away here. So that's basically, if maybe I take hydrogen from this, that simply means I'm going to take OH from that. You see, and then what will be left? I'm just going to draw the yield line from here down, going downward. And I'm going to write everything that is left here, the remaining. That's that. And then this particular part that is remaining, I'm going to merge it with that part that is remaining on the alcohol part. And then I'm going to say a plus because I just took what? H2O. Now, this is how we get to the name. Now, I said, what I wrote here, the alcohol part is going to get the YL part, the branch part. Now, we're going to check which part is the alcohol part, the part that does not have a C double bond O, which is this part this side. And then how many carbons are here? 1. So meaning we will be saying methyl. Methyl. The carboxylic acid part, which is this one, carbon double bond O, it takes the suffix of an ester. How many carbons are here? 1. Methanoate. Methanoate. You see? So, plus, obviously, water. So this is how we name the ester. We come to check here. We have the carbon part, the alcohol part, having the methyl part, being the YL part, and then the carboxylic acid part being the one that carries the ester suffix. Maybe this example is a bit easy. Let me bring something that can make you understand bigger structures. Let's draw this structure. Let's say we have a structure that is 1, 2, 3, 4. 1, 2, 3, 4, 5. And then I just add hydrogens and then whatever that is necessary. Nice. Now we are here. We check. This oxygen, I like to say it serves as if it's a bridge between the two, because after this oxygen, you are going to be met by two carbons. The carbon with a double bond oxygen and the carbon that doesn't have oxygen anywhere. So on each side of the oxygen, between this and that, you will be knowing the one that carries the ester suffix and the one that carries the branch or the YL suffix. Now let's check here. This side, how many carbons are there? 1, 2, 3, 4, and 5. Do you have oxygen from here to go that side? There is no oxygen. So we can say, what is the prefix of 5 carbons? Is pent. And since there is no oxygen or anything, we will call him pentyl. We come here, oh, we see here, there is C double bond O, meaning we having the part that has what? Going to take the suffix of an ester. Including this carbon, we will be saying 1, 2, 3, 4. So it's 4 carbons, meaning it's going to have a prefix of but. Butanoate. So meaning the name of this ester is going to be propyl butanoate. So repentyl butanoate. So that's basically how you get to name your esters, because you'll be able to see, oh, where I see pentyl, I know this part is alcohol. And then where I see butanoate, I know this part is carboxylic acid. This is as easy as it can ever be. Beautiful, easy, and just easy to follow. And I hope it's understandable for you to grasp without any having complications. And then if maybe you have any complications or rather you need me to do more, because in our next session I'm going to do structures that are super sophisticated, beautiful structures, and then also grab some few questions from the exam, and then we'll be dealing with answering all those questions, and then we are done with this part. We move to reactions, we move to any other topic that you want us to do for mathematics, physics, chemistry, and then we are just going to ride along. And then I hope this helped you. And then from the first one when we did alkane up to this last one, which I chose to be esterification. And if there's everything and that you do not understand, there is a comment section there. Please don't hesitate to ask any question. Thank you very much and enjoy your day.